Recording.
Thanks everyone for coming and sorry for the delay. So today we are really honored to have Professor Karthik Narasimhan as our speaker. So Professor Karthik Narasimhan is an assistant professor in the computer science department at Princeton University. His research spans the areas of natural language processing and reinforcement learning, with the goal of building intelligent agents that learn to operate in the world through both their own experience, that is doing things, and leveraging existing human knowledge, that is reading about things. So Karthik received his PhD from MIT in 2017 and spent a year as a visiting research scientist at OpenAI, contributing to the development of the famous GPT language model also. And then he joined the Princeton in 2018. He is the recipient of a Google Research Scholar Award in 2022, an Amazon Research Award in 2019, and the Best Paper Awards and nominations at EMNLP 2015 and 2016. Without further ado, let's welcome Professor.
Awesome, thanks, Wenlong. Hi, everyone, it's great to be here. So hopefully the audio is fine, right, Wenlong? I can only see you.
Yeah, we can hear you, thank you.
Okay, all right. So today I wanted to talk about, actually, maybe can you mute it? I'm getting sort of an echo.
Yeah.
Can you mute your laptop? Okay, awesome, thanks. Yeah, so today I wanted to talk about, some of our work in the lab around this broad direction of language-guided machine learning, which hopefully I'll set up and you can see what I mean by this. So obviously, this is not a surprise to most of you here, but there's been a lot of progress in NLP systems over the last few years, right? So right now it's on this exponential trajectory, and both in the practical sense, where we're having systems that can perform very good machine translation, voice recognition, personal assistance, you name it. But also, models right now, the state-of-the-art models are really sort of smashing these benchmark tasks that have existed in NLP for the last few years, right? And the funny part here is, even on these sort of benchmarks, we're now seeing models that are superhuman, beating these human baselines that are quite low in the leaderboard. And this is not even, this is probably an outdated screenshot that I took, a few months ago. So obviously, I'm not here to sort of just talk about what the state of the art can do, but what I want to point out here is there's sort of been this shift from in computational linguistics from the last few decades to where we are right now, in that modern machine learning and primarily right now, all the models are primarily using some form of deep learning, right? So modern machine learning here and deep learning predominantly is treating language as yet another modality, right? So if you take all the popular neural network architectures now, be it transformers, recurrent neural networks, graph neural networks, they are all basically, language agnostic models, right? So they don't really need to think about the linguistic structure. And they can all just basically be optimized using standard gradient descent techniques, as long as you have some NLP dataset, right? So even if you take models like BERT or GPT-3, they're just literally treating the words and phrases and so on as sequences of things, right? So this is all great, but what I want to sort of focus on and ask the question in this talk is, what can natural language instead provide for machine learning, right? So all of the advances that we're seeing here are machine learning tools, machine learning models, optimization techniques, really pushing the needle for NLP applications and NLP tasks. But what can language provide in the opposite direction, right? So can we make use of natural language in ways that help machines learn better? So this talk is basically going to try to give you some answers to this question, right? And hopefully convince you that there are certain things that we can use language for learning in machines. And I'll basically talk about two ways that we can use language to help machine learning, right? So first of all, language is a human construct, right? So there's lots of ways that humans use them, but in this talk, I'm going to basically focus on how language can help provide what I'm going to call semantic supervision, This will be clear in a few slides, but I'm going to show you how language can provide, sort of richer forms of supervision that can help machines learn better. And also how language can provide guidance for learning, whether it is for efficient reinforcement learning or safe reinforcement learning. And you may be asking the question, right? So why do you even bother about, to use language, right? So there's at least two reasons why we would want to use human languages. One is language provides this nice semantic structure, which again, I'll show you that is going to help learning. But more importantly, this is how humans communicate with each other, right? So we've been using natural languages to sort of share knowledge with each other, record our experiences, record our policies, record things that we have learned by interacting with the world. And if we can just get machines to understand language, they can maybe learn by reading, right? So they can basically source information that humans already know instead of learning everything from scratch. Okay, so hopefully that sort of gives you the high-level idea of where I'm going. And so without further ado, let me talk about the first piece of work, which is basically what we're calling semantic supervision. So this is a paper that was led by two of my students, Austin Hanji and Amit Deshpande, who are both doing a PhD over here. So to sort of motivate this problem, let me just recap the standard classification setup, right? So I'm sure all of you at some point have trained tons of classification models, where the basic idea that you have is your input is some piece of text or an image or whatever input that you're dealing with. And what you normally want to do in this classification setup is you're trying to output a class ID, right? So this can be things like 0, 1, and 2, where you pre-assign these class IDs to specific classes of interest in your own problem, right? And for the classification problem itself, your goal is to learn this function f from x to y, right? So you have whatever piece of input that you're going to get, and you want to predict one of these labels for as your class. So this is great, but what modern machine learning is trying to do here is like at test time, the idea is you generalize to new inputs x that were not seen at train time. So you have a training data set, you train your model, and then you're trying to generalize to these new inputs. But the key part here is like the output space of this function is limited to the IDs that you've seen during training, right? So you can train this model to predict 0, 1, or 2, but you can never predict a new class which might have been assigned to a 3 or a 4, right? This is the fundamental limitation of this kind of a setup, and this is true even if the class 3 or 4, this hypothetical class 3 or 4, is made up of concepts that the model already knows about, right? So the model in its classification learning of the parameters, it might have sort of picked up features that may be useful for this new classes, but it can never do this because of the limitation in the problem setup. So that's basically, if you think about it in some other way, what we're trying to do alternatively is trying to get the model to answer these kind of multiple choice questions where the choices themselves are fixed numbers, right? So be it image classification or text classification, what you're trying to do is ask the model, hey, pick from 1, 2, or 3 and tell me which class fits the input the best. So this, like I said, the limitation here is the output space is devoid of any semantics, right? So we're sort of stripping away the semantics and fixing these class IDs. So the model really has no idea in terms of like what the class ID represents, other than the fact that it has seen these patterns in the data. So traditionally, what would happen is model will basically imbibe this sort of class semantic. Sorry, 1 second. Let me just move this. This sort of class semantic information. All right, this works. Yeah, model basically sort of imbibes the class-specific semantic information at the task level, right? So it learns the features that are useful for this task, but you can't really do much in terms of changing your output space, right? So you try to change it, it's not really going to work. So it's not suitable for generalization. So with this setup in mind, what we want to do is just make a very simple change, right? So instead of showing these questions that are basically just class IDs, can we provide more semantics in the output space, right? So instead of having these choices be integer numbers, let's just make them, for example, descriptions of the particular classes themselves, right? So here you have descriptions of a dog, a tiger, and a fish, right? And basically, these are descriptions that you can get from anywhere. I'll talk about how we get them in this particular task itself. But the high level idea is you're basically now trying to allow the model to read its options before trying to pick one, right? So this is basically something that we as humans do all the time, right? So this is natural to us when, let's say you have these multiple choice questions in an SAT exam or a GRE exam, right? So with this simple change, right, so that you sort of get a lot of advantages in this setup. So first of all, you can vary the number of choices between train and test, right? So you don't have to be limited to 1, 2, 3. You can now maybe give 10 choices, right? As long as the model can read all of them and then pick the one that is most relevant. The second thing is that you can now describe these different choices in different ways, right? So let's say I have a different idea of what a tiger should look like in my data set, then I can come up with a different description for tiger. And as long as the model has an understanding and a grounding of what these different attributes mean, it can hopefully generalize to these new descriptions, right? So this is something that could be very useful for personalizing your model or correcting the model, right? So it sort of gives this extra dimension of interpretability. The other thing that this sort of provides is new concepts can now be provided as choices in terms of known terms, right? So let's say the model has never seen a zebra or a unicorn even, right? It's a mythical creature, but you can still describe it in terms of things that the model knows about, which are stripes, what are wings, what are horns. These are things that it hopefully sees in the training set, and it can now generalize to these new classes. And then the final thing is like you can even, sort of span different levels of granularity, right? So you can now just, during test time, let's say you want to classify between tigers and reptiles, hypothetically, you could do it by simply providing a description of what a reptile is. And again, because the model hopefully gets a better sense of the fine-grained semantics of each class, it can generalize to these new classes. Okay, so that's basically the high-level idea behind our work. So we call this overall framework semantic supervision, and this figure sort of gives you an idea of like how this differs from the standard supervised setup itself, right? So the top part is showing you how standard supervised setup looks like, but what we're doing is replacing these class IDs with descriptive choices. So I sort of had this running example that's using English text to describe these classes, but it doesn't have to be English text, right? So you can describe classes in whatever way you want. You could, for example, even use programmatic language like JSON to describe your classes, and that's totally fine as long as you're providing extra semantics on what the class actually means. So like I said, the model basically has to read these choices and pick the appropriate choice for each input. So basically performing classification in this way. And this basically allows for generalization over both the inputs, which is the standard supervised assumption, right? So you're generalizing over these inputs, but also over outputs, where you can now change your output space as long as you can describe it in English or JSON or whatever output format that you decide. Okay, any questions at this point before I talk about the modeling and what we do? Is the overall framework clear?
Yeah, there's
Okay.
a question.
Sorry.
Yeah.
Who provides the label?
Who provides the labels? The question is.
Who provides the labels? Okay, I will answer that in a few slides.
Okay, any other questions? Okay, I think we're good. Oh, one more. So how does this relate to clip embeddings?
Okay, I also have that in a couple of slides. Good, okay. All right,
Good.
so let me first talk about how we would train this kind of a model in a general sense, and also talk about how this relates to clip and other sort of paradigms, right? So with this setup in mind, right? So we basically have any sort of input and any output class that is described in these terms, right? So the way we can, I mean, this is just a simple model that one can do to train this kind of a SEMSIP model, right? So basically what we have is you have your standard input encoder, let's call it F. This would be there even in the standard classification setup. Now, in addition, what we're going to do is we need some encoder that can encode these text descriptions, right? So you can use models like BERT or Corberta. We basically experimented with different variants of these, but the idea is like you're basically encoding each of these class descriptions into some vector format, right? You can even do it without any pre-trained model. That also works pretty decently well. But the idea is like once you encode these into these G vectors, we then just basically have projection matrix that can be used for bilinear scoring between F and G, right? So you project it onto this P, and then you get some logits which you can feed into a softmax that can then be basically used to get a probability distribution over the provided semantic trust, right? So not much, it's a very simple model. All you're doing is sort of having this encoding at the output space that provides a way to encode this into the vectors. So this is the simplest model. We have some more complicated models in the pipeline, but I won't talk about those. But the high level idea is like you're basically trying to use the semantics both in the input and the output space, and then decide which class matches your input the best. Okay, so for training, there's not much that changes. You can use gradient descent as you would for a standard classification setup. The interesting things that we found is that you can actually train this model using multiple descriptions per class. So this is useful because there are probably different ways of describing a particular class, right? So a tiger can be described visually in terms of its habitat, in terms of what it does. And all of these can provide useful information about what that class actually is semantically, right? So we train it using multiple descriptions. So coming back to the question here, we collect these descriptions basically in a semi-automatic manner from the web. So the exact way that we did this was to, query search engines like Google or DuckDuckGo, get definitions from, web results. And we actually found this to be pretty, pretty decently, automatic and pretty easy to collect these. The only sort of manual effort was to make sure that you need to disambiguate sometimes, the meaning of a particular term, right? So if you have something like a bank, you need to do word sense disambiguation to make sure that it's a financial institution versus, the bank of a river or something like that. But other than that, it was pretty easy to collect these descriptions. We didn't really do any post-processing. There is noise in these descriptions, and that's totally fine. The model handles all of that. And for JSON, we basically used something like a knowledge base and converted it into the JSON itself, JSON format itself. So you could probably get it in many, many different ways. Okay, great. So during training, we basically use multiple descriptions. We just randomly sampled one description per class. There's probably other ways you can train this, but the idea is, enable the model to capture these different aspects that are represented in these different descriptions. So right, so basically that's the high level idea of the SEMSIP model, right? So during training, we can basically train using the cross entropy loss, using these sampled class descriptions, right? And then make predictions. And of course, you can train models using these flexible types. It doesn't have to be only English. You can use different languages, maybe. You can use things like JSON. And then during inference, right? So this is sort of like the classic classification setup. You can use unseen class descriptions, right? People may describe it in different ways. You can also use unseen classes. Let's say you've not seen a penguin. As long as you can describe it, the model can generalize to it. And you can also use unseen granularities, right? So depending on your use case, it's a very flexible model as long as you've trained it on concepts that you think are useful for your task. So, right. So concretely, right, so there are these 4 generalization capabilities that we talk about in the paper itself. So I mentioned some of these, but just to sort of summarize, the SEMSIP enables generalization to these various scenarios. You can generalize to unseen descriptions, unseen classes, unseen superclasses, and also even unseen tasks. So when I talk about unseen tasks, I'm basically saying cases where you can have a totally new set of classes that you want to predict over, right? And which have no overlap with the training classes that you've seen. So this is an extreme scenario, which I think not many works have looked at. And so this figure here is basically showing you why this should work, right? So basically at a high level, we're trying to learn this like giant input-output space. There's of course been work trying to do this. So I'll answer this clip question right now, but the high-level idea is like, as long as we can embed both of these into the same space, we should now have a way to generalize over the output space as well. Okay, so right, so let me just quickly address some related work, right? So obviously, a lot of work has looked at zero-shot learning with auxiliary information. So these are just a bunch of them. There's more that I couldn't fit in the slide, but there's work that's looked at different ways of specifying classes using, let's say, images, word embeddings, text from Wikipedia, and all of these works have basically looked at using simple methods like word embeddings and so on. And concentrating on just having one particular description that is the definition of a class itself. So we're trying to just do it in a broader sense. You can sort of describe classes in any way that you want, whereas these we're trying to augment the ID with, let's say, the class name, for example, right? There's also work that looks at class attributes, so not necessarily using language, but it's kind of related because they're using attributes which may be sort of vectors of concepts, or additional attributes that provide some side information that is also useful for classification. Work looking at natural language explanation is also sort of relevant because you're trying to predict the explanation for a class, and that helps you learn the problem better. And then there's also work on learning with manuals, right? So this is more on the RL side, but here we also have work that has looked at using descriptions of the task itself to help you learn better policies. So coming back to the specific question of CLIP, right? So CLIP is definitely relevant. So in some ways, I think of it as one particular instantiation of what we're doing here. First of all, CLIP is text image only, right? So it's looking at this problem of matching images to their captions. Whereas what you're saying is like you take any classification problem and literally just change the output space to have descriptions, and you can sort of gain some things and not lose anything. CLIP is also focused on just using captions describing the scene. It's not allowing you to describe different properties of a class. So in that sense, you're not getting fine-grained descriptions of what the class means. And of course, the CLIP model itself is doing this large-scale pre-training. So if you want to use it for your own task, let's say X-ray, chest X-ray classification or something like that, it probably doesn't do well, which is also something that they talk about in the paper itself. So what we're trying to do here is basically say you take any classification task, just convert this by using descriptions, and you will gain something in terms of generalization. So there's also other work that might be familiar to you, right? So you may also ask the question, how is this different from language model prompting? So this is like a new paradigm that is quite hot in NLP right now, right? So language model prompting is also, a sort of a subclass of what we're talking about here, right? So where you're basically having text-to-text classification, right? And also relies on this large-scale pre-training, and usually these prompts are either high level, right? So you basically have a sort of input, and then you say this is a blank, and ask the language model to fill in the class itself, right? So you're not really giving it descriptions at a fine-grained level. Or even if you had to give descriptions of a class, which you can probably do by fitting in the class description and looking at the perplexity, you sort of require multiple passes, right? So let's say you had 100 classes, you would basically have input concatenated with the class description and run it 100 times, and then figure out which one is the max or min perplexity, and then choose that as your prediction. So I just want to pause here to make sure I answered the question on CLIP. Is it clear in terms of how this is different?
Yeah, it's clear.
Okay, all right. I'll take that as yes. Okay. Oh, yes. Okay. Great. So with that, let me just show you a couple of results from our experiments to show you how this works in practice, right? So we did these experiments on 4 different data sets. A couple of them are text classification data sets, and a couple are image classification data sets. Of these, I think RCB1 is the one multi-label classification data set. And in terms of output supervision itself, right? So what we did was for the English descriptions, we basically converted class names into queries, like I said, and got the resultant, scraped the resultant descriptions and performed some level of manual filtering to remove these word noisy descriptions due to disaggregation. We also use these attribute sets provided in data sets like AWA2 to create JSON with the types as keys and actual attribute lists as values, but you could probably get these in different ways from any knowledge base of your choice. So the models themselves, I'll just show you a few of these models that we compared to. There's probably more coming up in the paper, but there's 3 different variants of SEMSUP you can look at. One is that SEMSUP all that uses all these class descriptions, but you could also just focus on using just a single description or using just the names, right? So this is basically a variant of prior work that uses class names instead of descriptions, but we use the state-of-the-art BERT models and so on to update that. There's also these prior work models like Device and Guile, which are sort of most similar. I didn't get a chance to include some more results from models like CLIP, but I can tell you they don't perform as well. They're actually worse than these Device and Guile baselines, at least in some of these tasks. I think on one of these tasks it's pretty competitive, but on the other it's. So these are sort of the results on these different scenarios. So before I show you results on scenario 1, which is the unseen descriptions, a quick point here is that if you use these models, all these models, including SEMSUP, on just standard supervised learning, right? So you don't care about generalization, you don't care about zero shot. The scores are basically matched with a standard classification model, right? So at the bottom here, I'm showing you scores that a standard supervised model gets: 96, 92, 74, and 94. And if you just literally replace the class IDs with descriptions, you lose nothing. The SEMSUP model gets exactly the same scores. So basically, you're not losing anything in your standard in distribution test. And so with that in mind, right? So let's see how you can get different forms of generalization. So first of all, this is the results on unseen descriptions. So the idea is, you've seen certain descriptions during your training time, but at test time, you are seeing potentially new descriptions of the same class, right? So this is something like, you train a model, you just give it to your friend, and they decide to come up with their own descriptions for the classes and use it in their own application, right? So over here, you can see the baselines, blue and orange. Device and Guile are not as good at dealing with this, presumably because they are not able to make this fine-grained mapping. But you can see SEMSUP, even the basic model, is able to get much higher scores and generalize these new descriptions. And so the delta here, right, if you look at each of these with the delta with the numbers at the bottom, so you sort of lose some percentage points. So RCB, you're losing 5 points, but on something like 20 news groups, there's no difference. CFAR, you're losing 3 points, and AWA2, you're losing 1 point. So even with unseen descriptions, the model is not losing too much compared to the standard supervised setting. Okay, you can also test this model with new classes, like I said, right? So let's say you've seen some classes during training time, and there's unseen ones that are now described in text. So again, you can see that SEMSUP does a better job at generalizing than the baselines, but overall the drop is kind of significant, right? So we are seeing some drop in the overall accuracy, and this is like a general problem in zero-shot learning. It's not obviously matching the standard supervised numbers, but it's still much closer to them than the baselines. And then the other, the third result that I'll just quickly show you is generalization to superclasses. So the idea here is you train it on classes that you've seen before, classes at a particular level of granularity, but then you test it on a level that is one level higher. So let's say you train it on things like dog, cat, parrot, and eagle, but then at test time you want to ask it, is this a mammal or a bird, right? So over here again, you see sort of the baseline's not doing as well as SEMSIP. So this is sort of an interesting use case, I think, because you can flexibly vary the output space partition, right? So in some sense, you think of the entire output space of things that you want to predict over, and you're making these partitions when you're deciding a particular task, right? So you can now flexibly change how you make these partitions and decide their granularity at test time. And if you have stronger models in using this SEMSIP paradigm, right? So we'll be able to do a better job with them. Any questions on these? Okay, I will take that as a no. So let me just quickly show you some auxiliary results too. So I mentioned that we use multiple descriptions during training, and this actually makes a difference. So this is an example on RCV text classification, right? So this was actually one of the findings that we had. When you use these multiple descriptions, you're much more robust and you're able to generalize with higher numbers on unseen descriptions or unseen classes. This is also another point that prior work did not really explore. They were just using the first line of Wikipedia or something like that. And so using more descriptions generally makes your model more robust. And this makes sense because you're giving it more semantic information about the class itself. And then we also did a quick experiment on the comparison between natural language and JSON. At least with this particular data set of AWA2, the animals with attributes image classification, we found that JSON is slightly better. Again, this may depend on your task, right? So I think JSON gives you more specificity. You're able to specify things more accurately. But natural language might just be easier to collect for other tasks, right? So depending on your task, you could see a variance in this particular aspect. But here, at least, we found that JSON was better. Okay, so this is sort of giving you a high-level idea of like what SEMSIP is and how it can be used for generalization, right? And so one caveat that I want to sort of mention here is, even though it can be basically used to convert any classification problem, it's not equally giving you this added advantage for all classification problems, right? So if you had something like sentiment analysis, I wouldn't use SEMSIP because even though you don't lose performance, it's not useful because you literally have 2 or 5 classes, right? So if you just have positive, negative, you're not going to get too much, right? So where SEMSIP really becomes useful is when you have a large number of classes and classes that can be described in several different ways, and that's generally a harder classification problem because the output space is much bigger, right? So in order to test this at the extreme level, right? So what we did was actually with some follow-up work, which was done with one of our interns, Pranjal, along with Amit, who's a PhD student here. We took this SEMSIP model and applied it for the task of extreme classification. So extreme classification is basically a setting where you can have a very, very large number of classes that you want to predict over, right? So this usually ranges in the tens of thousands to even millions, right? And so the interesting part here is an extreme classification, has several real-world applications. So you can use them, for example, in e-commerce product tagging, news article classification, and search engine results, and so on. And the interesting part here is that because the class set is such a large space, it also rapidly changes over time, right? So if you think of something like news article classification, an example is, COVID-19 basically came up in 2019, and you immediately had lots of articles that fall into this class, right? So you want your model to be able to quickly generalize to these new classes that come up every month or every day. So what this makes crucial is the fact that you basically want a model that can handle these large spaces, but also be able to perform zero-shot or few-shot classification. So what we did in this work, right, so this is still under review, but what we did here was basically to scale up SEMSIP to these larger classes using three techniques, right? So first of all, we basically came up with an automatic class description collection mechanism that's able to query the search engine, apply heuristic filtering. So that we basically have a mechanism to remove the manual effort that is required. And this is crucial because you want to get these descriptions for 1 million classes. And then on top of that, we basically have two technical parts that we added to the model. One is contrastive learning. So instead of using cross entropy, you can sample negative classes and it still works with the SEMSIP framework. And we also use this lexicosemantic matching module, which is basically a variant of COIL, if you know about COIL-BERT. But we basically use this module to help further refine the fine-grained matching that the SEMSIP model performs itself. So I won't go into details, right? But just to give you a quick idea of the results, right? So we did this over 3 different data sets, right? So these data sets, like I said, have thousands to millions of classes. These are pretty well-established data sets for this direction of extreme classification. And this is one sample over here. You can see already, right, like precision at 1 compared to state-of-the-art models, including the Mockclear model, which is, which was released just over the summer. You can see that SEMSIP provides quite a big boost in terms of precision at 1, almost 13-point boost over the Mockclear model. And then you can also use this for, few-shot learning, right? So those results were on 0-shot, but as you get more instances per label in the test set, you can see that SEMSIP also scales pretty naturally, and you can see that the blue curve here is quite higher than all of the different baselines. So this is on, I think, Eurolex 4.3K, but you can see again, right? So the 0-shot number is already higher than the other baselines, but it sort of maintains it as you give it more data, and getting as high as more than 70% with just 20 instances, while the baselines are less than 60. Okay, any questions on SEMSIP at all before I move on to the next part? That was basically the end of part 1.
Hi, thanks for the great descriptions. I was hoping to go back to the scenario where you were looking at unseen descriptions during test time.
Yeah.
And you said that there was a gap. It wasn't large, but it does exist. I was wondering if you looked at any qualitative examples of where the gap lies, and have you analyzed that at all?
Good question. Yeah, so we don't have quantitative numbers on this. We did look at some examples. I think the gap mainly arises from the fact that the baseline models use more simpler representations. Either they're trained on just like a single description, or they use sort of these bag of vector embeddings, and that doesn't really generalize when you have descriptions that talk about things in different ways. So I think that was one of the reasons. There could be other reasons as well.
Yeah, okay, thank you, Professor Narasimhan.
Okay. All right, so basically, I'm really excited about this extreme classification direction because, again, like I said, scaling this up to lots of classes has been a challenge for standard classification methods. But I think with this kind of a thing, right, like ideally I would envision, you just have this fluid output space where you don't really think about classes as these discrete partitions, whereas you basically learn the semantic structure over all things that you can describe, and basically use it for any partition that you decide at test time. Okay, so that was one example of how language can help learning in the supervised classification setup, right? So then let me just sort of switch gears into more of reinforcement learning, right? So for those of you who've worked on reinforcement learning, you've obviously seen some of these biggest achievements that you can call of DeepRL in the last few years, right? So we've seen achievements like AlphaGo or the Rubik's Cube demo that OpenAI had. And these are all impressive advances that DeepRL has given us. But if you have tried to train your own RL agent, right, you sort of know how frustrating it is to watch it try to learn, right? So this is an agent that's trying to land this particular spacecraft in between these two flags, but it takes millions of tries before it can actually do something reasonable. right? And sometimes this is not even a matter of frustration. It can even be downright scary, right? So this is a robot that's supposedly learning to flip pancakes, but you don't want this kind of a thing happening where it's basically just harming itself, right? So the key question here is that RL algorithms are great, but they're not very efficient, and they're not as good as humans at learning through both doing and reading, right? So if you really think about this example of the lunar lander, humans actually performed a very similar task. They landed a spacecraft on the moon, and they didn't get millions of tries, right? Not even hundreds of tries. We literally got 1 or 2 tries, right? So how did humans do this? Because I think they were successful not because they also used information in addition to learning on the go, right? So for example, humans have this knowledge that flat surfaces are stable, and you probably want to choose a flat surface for landing your ship. You know that the gravity of moon is 1/6 of the Earth, and so on, right? So we just don't explore randomly. We use our prior knowledge to guide our exploration, and we choose policies that actually are constrained in some sense based on our knowledge of how the world works, right? So the question now is, can we get machines to do similar things, right? So can we get machines not just to learn through just doing and this sort of trial and error paradigm, but instead also use information that could be present in text in various forms in order to learn faster and better. So right, and so the sort of premise here is, right, real world reinforcement learning requires us to think about things like safety, right? So it can be sort of physical safety when you're training a robot. You don't want it to hurt people or hurt other things around it, or even hurt itself. And it could even be safety in the virtual world, right? Like you train a bot that learns from interactions on the web. You probably want to make sure that it has some constraints that prevent it from going out of control. And this is not a new field, right? So people have been thinking about reinforcement learning with constraints in various ways. And the high level idea is, you basically try to provide the system with some constraints that are specified in a logical form or math or cost functions, right? So work like Akiyam's CPO and Fisak et al., they basically try to specify these kind of distance measures that look at constraining how the policy changes over time, right? So you have one episode in your particular environment, and your policy obviously changes as you're making updates to it, but you try to constrain it by specifying these kind of cost functions that make sure that you don't go beyond the boundaries, right? So in the Fisak example over here, they basically set constraints that prevented this quadcopter from flying into windy areas, right? So this is all great, right? But the key problem here is specifying these constraints is not easy, right? So this often requires expert knowledge, right? Only if you are into ML and into reinforcement learning, you will understand these cost functions. And they are time consuming to get, right? So you need an expert to be able to specify these kind of constraints. So what we ask as an alternative is, like, what if you just specify safety constraints in natural language, right? So this would open up personalization and safety and control to a lot more people than just ML developers, right? And this is basically the sort of premise for our paper, which was published in New York 2021. This is led by Jamie and Michael, my students. And the high level idea is basically this, right? So we're trying to do safe reinforcement learning, but using natural language constraints. So how does this look like, right? So before I talk about the paper itself, I briefly want to mention some advantages and disadvantages of doing this, right? So advantages, obviously, like I've sort of alluded to before, is natural language is easy to specify. It democratizes things, right? It's faster to obtain, it's end user friendly. You can bundle constraints with instructions, right? So you can tell the agent or a robot what to do and also not what to do. But there are drawbacks, right? So the NL can be ambiguous at times, the language, right? And it may not be precise enough for certain types of specification. So it's up to you in terms of choosing which applications can actually be used for this particular paradigm. So what do we do in this paper itself, right? So we basically come up with a benchmark and some methods that show that it is possible to use natural language to constrain policy learning in these RL agents, right? So what we do is we just basically come up with a grid world environment. This is based on mini grid, if it seems familiar to some of you. And so the idea is, there's this grid of squares, and there's an agent that has partial observability, but it tries to move around and collect these objects to get a reward, right? So objects here are like a key, a ball, and a ladder. And this is a standard RL setup, right? And on top of that, what we do is we also provide the agent with some constraints in language that tell it what not to do, right? So these constraints can either be budgetary, relational, or sequential constraints. So budgetary constraint basically tells the agent not to do something more than n times. So something like don't walk on lava more than 3 times, right? A sequential constraint can be saying that, if you walk on grass, you're then protected from lava, right? So basically different ways of specifying what the agent should be aware of and what it shouldn't do, depending on its actions in the environment itself. So how does this sort of compare to instruction following, right? So as some of you would probably be aware, instruction following it has a long line of work, right? And I just want to quickly point out that the main differences here are, first of all, constraints are auxiliary, right? So if you don't have these constraints, that's totally fine. The agent can still learn the task. But what we're trying to do is provide this auxiliary guidance to help the agent learn in a safer manner. Rewards here are not going to be correlated with constraints provided in the language, right? So the agent's reward is still going to be if it picks up the key or the ball or the ladder, and that's how it is in instruction following. But here the constraints are orthogonal, right? So they're trying to specify something other than the policy's goal of getting reward. And the final thing, which I think is really the best use case, is a set of the same constraints can be applicable for several different tasks, right? So right now, if I just change the objects, instead of say pick up the key, I add a new object and tell the agent to pick that up, like a green key or something like that. These constraints are still can remain exactly the same, right? So it can still learn to avoid lava or use grass to protect its boots and all of that, right? So even with objectives being completely different, the same set of constraints can be applicable to several different tasks. And this is sort of similar to, in your own home, right? So let's say you have a humanoid robot in your home. You tell it something like, don't go near the TV because you think it's going to break the TV. That should apply regardless of what the robot is doing, right? So whether it's cleaning the floor, rearranging your furniture, or bringing you water, doesn't matter, right? As long as you want it to follow a specific constraint, it should be able to respect that. Okay, so I guess very quickly, what are the key challenges here? So first of all is how do you ground and represent these constraints in text, right? So for a human, it's easy to read these constraints and follow them, but not for an RL agent. And then how do you use these constraints with reinforcement learning to learn safely, right? And then the third sort of challenge is how do you obtain this kind of a data to train the model to interpret these language constraints? And so our approach is basically trying to answer these 3 questions. So first of all, we use a meta learning approach to train this constraint interpreter that basically converts text into tensor representations, right? So basically, the idea is you have this safety training phase where we're training this constraint interpreter and policy network to understand what these constraints mean, right? So this is basically just giving it some episodes to understand how to interpret these constraints, where we're not really thinking about safety. But after that, we can combine this constraint interpreter with standard algorithms that are used for policy learning. So this can be things like CPO, PCPO, and other algorithms. So the main difference that we have to sort of take care of is how to use noisy predictions from the constraint interpreter with these algorithms that expect exact values. And for the constraints themselves, we basically collected it in English by asking characters to specify these kind of constraints. Okay, so Right. So like I said, there's basically 2 stages. So during safety training, the entire goal is to learn a constrained interpreter that can perform this kind of a grounding. And the task is actually during, the agent is evaluated in this safety evaluation phase, where we give it a new task, right, where the reward structure is completely different. But the idea is the agent has to now follow these constraints. The constraints can be different as long as they're within distribution. They're of course different in terms of the exact text. But the idea is the agent has to understand them and follow them as it's learning this new task. Okay, so let me just quickly give you examples of how these look, right? So like I said, we have this grid world environment. We collected more than 3,000 textual constraints that we paired with 25,000 different maps. So you have a lot of different train and test environments. And we made sure to separate the train and test tasks, right? So you don't see the same reward function or objects at test time compared to train. This is one particular variant that we call Hazard World Grid. There's another variant called Hazard World Robot, which has a different environment itself. But the examples like you see over here, right? So they're just text that a Turker wrote on Amazon. So it's not templated or anything like that. Okay, so I will maybe skip the technical part of this, right? So there's a lot of deep learning architecture modeling choices here, but I'll just quickly show you what the evaluation and the experiments look like. So like I said, we have these two benchmarks, Hazard World Grid and Robot. The metrics that we care about are twofold. One is the return, which is the reward that you would normally care about in an RL task. But now we're also caring about the number of constraint violations that the agent performs on average, right? So we want this constraint violation number to be as low as possible, close to 0, ideally, and the return to be as high as possible, because we want it to get maximize its return, basically. So for baselines, we took some baselines from instruction following. There's a random walk, which is a simple baseline, but basically constraint fusion is an instruction following method, right? So that takes language as just an input, right? So basically taking the grid as input and the language, the constraint text as input, and combining them in a fusion architecture. This one is basically to demonstrate that simply adding language as input doesn't work, right? So even though we use a PCPO, which is a constrained learning algorithm. So that's one baseline. And then we also have constraint fusion with TRPO, just to show if you use an algorithm that doesn't care about constraints, what would happen, right? So the last baseline here doesn't care for the constraints at all. So here's an example result, right? So there's more in the paper, but this is an example of results on budgetary constraints on Hazard World Grid. So as you can see, POCO, which is the red bar over here, gets the most reward while having the lowest constraint violations. And you can also see CF with TRPO gets the second highest reward, but it's pretty high on violations because it doesn't really care about the constraints. Okay, and a similar thing in the robot case, but I'll let you look at more of the results in the paper itself. Okay, and then I just wanted to quickly point out, right? So you can also do this kind of learning from manuals, not necessarily only for SafeRL, but you can also do this for efficient reinforcement learning, right? So this is something, again, it's very recent work that our lab had in collaboration with Ani Majumdar's lab here. The idea here is, we're trying to get robots, this is all in simulation, but we're trying to get robots to learn about new tools and how to manipulate them. And normally you would just get them to have these different episodes with these new tools. But what we are doing here is to have these meta training approach that uses natural language descriptions. So the idea here is, again, if you have descriptions that talk about how a tool looks like and what it's generally used for, the robot can adapt its control policy faster than if it had to adapt without having these descriptions, right? So you sort of train this during the meta training phase, you can train it with some tools, and then during the test phase, you can give it new tools that it's never seen before, right? Like a paint roller that is cylindrical in shape and so on, right? So the idea is like, if you're given this description, then the robot has to understand how to do a task with this paint roller, for example, how to hammer a nail with the paint roller, right? So if you have these descriptions, it helps the robot basically understand how to grip the particular tool and also how to use it in terms of performing the task itself. Okay, so basically I'll end here. So in summary, right? So what I've basically talked about is different ways of looking at language, natural language to help machine learning, right? So the first part was looking at this supervised setup where we can use language to describe classes and provide more semantics on the output space. But it can also be used to provide useful knowledge for more efficient and safe reinforcement learning, right? And of course, this is just like scratching the surface at this point, right? So there's a lot of interesting future challenges. How do you look at different types of information that are conveyed? How do you understand all of this in more context, such as visual signals and other haptic signals and so on? But I think there's some promise in basically looking at language as a way to communicate human knowledge, right? So as long as we can get agents to understand language, we can really reuse a lot of human knowledge that's available and make machines learn more efficiently. So I'll stop here. Thanks to all my collaborators. If you want to look at some of these papers, they're all available at the website. Thanks.
All right, thank you so much, Professor Narasimhan.
Yeah, happy to take questions if there are.
Yeah, I think it's a wonderful talk. It's really joyful to hear these cutting edge technologies being connected and all those possibilities being opened up. We're slightly past 1, so let's see, maybe we can take 1 or 2 questions if there are any. Please feel free to just speak up. We have the voice lift system open, so yeah. Yeah, go ahead.
How do you connect constraints to the file, as a particular description? You have to select constraint in terms of model, and I assume somehow my question is how does that be done?
Sorry, I couldn't hear it. Could you repeat, Val?
Yeah.
So my question is about constraint interpreter, and my question is how it connects constraint description to tiles. Do tiles have description and it connects somehow? Maybe it was in skip part. So my question is how constraint interpreter connects constraints description to tiles and probably tiles description.
Yeah, I had to skip over the exact architecture, but yeah, we basically have it predict these things actually. So there is a module that predicts a mask over the entire grid, for example, that predicts the absence or presence of constraint related entities like lava, grass, or all of that. There's also something that predicts the budget remaining as well as the safety threshold. So yeah, I had to skip over this, but yes, we do predict all of that and learn it through the reinforcement itself.
Thank you.
Thank you. Other questions? Yeah, if you don't mind, you could come up. Sorry that it's unusual setup.
Do we see any improvement in convergence speed? Does reinforcement learning converge faster if we add these natural language constraints? Thank you.
Yeah, no, this is a great question. So this particular work was more focused on safety, but there is other work both in our lab and otherwise, right? Which looks at using these manuals to improve learning speed. So I think it sort of started back from Branneman's classic paper in 2012, where they did this for civilization. But there's been other work also that looks at basically using manuals, and it does help speed up the learning process itself. So there is a startup cost again, right? So all of these, the assumption is how do you learn this grounding between symbols and language to the observations that you see in the environment? But once you learn this grounding, I think there's sufficient evidence to show that you can learn faster. So the key problem again is how do you learn this grounding and make that efficient?
Yeah, thank you. Other questions? Yeah, if not, let's. Oh, yeah, please go
I
ahead.
have a question. So when you have these, so when you have specified these constraints and you show that your methods violates less constraints, does it mean that the final policy learned by your method violates less constraints, or is it that the exploration process was also more safe?
Yeah. So this is all with the final policy as well, but also during exploration, the average number of violations is lower.
That's good. That's really cool.
Yeah. So you want to make it low because exploration is where usually this kind of
Exactly. Yes.
problem arises, right? But again, just to make sure, right? Like we do have a safety training phase, which is crucial to getting grounding. But then on a new task, you can have less violations.
Okay.
Yeah, if there's no more questions, let's give Professor Narasimhan another round of applause and thank him for the wonderful talk.
Okay, thank you so much.
We'll see you next week.
All right, bye everyone.